Well, so let's get started. This is the second of my 4 lectures on holonomy, and of course yesterday you saw the 3 different talks, 3 different definitions of connection. It was that was not completely unanticipated in our plans. I don't know how many of you ever made it to the end of Spivak's 5-volume work, A Comprehensive Introduction to Differential Geometry, but you know he has notes at the end about various things that, in spite of the fact that it's comprehensive, he didn't have time to cover. And one of those was he didn't have time to cover all the different definitions of connection, in spite of the fact that Volume 2 is essentially devoted to all the different definitions of connection in the Riemannian case. What he says at the comment that he makes at the end is personally I feel that the next person to come up with a new definition of connection should be taken out and summarily executed. I was visiting him one time, and he actually showed me the file of letters that he got after that volume came out of people complaining about his not having covered their favorite definition of connection. I think one of his favorites was there was a letter purporting to be from an 8-year-old describing how one could understand connections in the language of category theory, and of course that's not quite as funny now as it used to be. Now that physicists are telling us we have to really learn category theory and take it seriously. Anyway, without any further ado, I remind you of this list of possible holonomies that can occur in the non-symmetric case, irreducible holonomies that can occur in the non-symmetric case, and most of the rest of the lectures are going to be about the various different geometries, the geometric features that these special kinds of manifolds inherit from having a special holonomy. And what I wanted to do today was sort of set the stage for the more interesting, well, the more exotic ones down in the lower part of the list by discussing some of the ones in the upper part of the list, ones that presumably you're a little bit more familiar with, ones that have been studied more intensively from mid-century on, and develop a few of their features today, and use that as a springboard, sort of as a framework to see how different features show up and can be used to study the cases, the more exceptional cases, G2 and spin 7, and even the very interesting nowadays case of so-called hyperkähler geometry and quaternion Kähler geometry, these 2 things associated with the quaternions. So I'm going to start, so in fact today is really going to be about these 2 cases, the unitary and special unitary, and of course Kähler geometry and nowadays called Calabi-Yau geometry is a big industry in differential geometry, and there's no way I could cover everything, but what I'm going to do is say is try and give you some background, basic things, like I said, set up a framework, and besides, I mean, we're having a whole lecture series on complex geometry anyway, and that should you should go to that for more detail. So I'm going to start talking about unitary holonomy, and in this particular case, I'll remind you, just to get started, how we're defining the unitary group sitting inside the special orthogonal group. What we do is we endow R2n with its standard inner product and orthogonal complex structure, and then the unitary group is, of course, the set of special orthogonal matrices that commute with this almost complex structure. That is, they're the complex linear special orthogonal transformations, and such a thing, this condition, as you can easily see, forces the matrix capital A to look like this, where little a and b are n by n matrices. And if you just identify this 2n by 2n matrix with this n by n complex matrix, then this is in fact a homomorphism, an embedding of this group defined in here into GLNC. And so from time to time we'll think of this either as matrix 2n by 2n matrices or n by n complex matrices. Now, if the holonomy of a metric is conjugate to a subgroup of UN, that's what we'll call unitary holonomy, then by definition M possesses a parallel almost complex structure. That's what it means. That's how we define UN. And that parallel almost complex structure, because it's orthogonal and therefore skew symmetric, it corresponds to a two form. And the usual way of turning a skew symmetric matrix into a two form, you just plug it into G. This defines this two form, and because G is parallel, by definition it's parallel with respect to the Leibniz-Civita connection, and J is parallel, omega is parallel as well. And in fact, this equation, this particular equation determines, for any two of these, determines the third. Obviously, you can read off, obviously omega is defined in this way. If omega is defined, then and G is defined, then J is defined. And similarly, if J is defined and omega is defined, then G is defined by this equation. And that's going to allow us to turn things around. Instead of thinking of the structure as defined in terms of a metric with reduced holonomy, we can think of it instead as a structure on the manifold where, say, J and omega are given and G is then determined algebraically from them. The fact that J and omega are parallel with respect to G implies two things that are important. One is what we already saw: parallel form with respect to any metric is closed. In fact, it's closed and co-closed. So that's the first thing that you get from the parallelness. The second thing is a statement about J, which is that J is integrable. As you know, an almost complex structure is not in dimensions 4 and higher is not necessarily given by a complex structure. That is, I mean, to say that an almost complex structure is integrable says that you can always choose complex valued coordinates. You can cover M with coordinate neighborhoods, so complex valued coordinates that carry J out, in the differential, which is, because this is a diffeomorphism, the differential gives you an isomorphism of tangent spaces, so it allows you to conjugate J out to simply multiplication by I. That's what we mean by saying that such coordinate systems are said to be holomorphic with respect to J, or J holomorphic. And for J to be integrable says that there exist such coordinates everywhere. Let me just give you an idea of why these two things are true. First, we already saw that omega is closed. That was this completely general statement about parallel forms being always closed. And remember, the basic idea behind that is that the exterior derivative is made out of in any coordinate system, the exterior derivative is expressed in terms of first derivatives of the coefficients. But if it's parallel with respect to a metric, then that means that, for example, in geodesic coordinates, the first derivatives will all be 0. And since the first derivative's vanishing forces the exterior derivative to vanish, that's first derivatives in some coordinate system forcing the exterior derivative to vanish tells you that the exterior derivative vanishes anyway, because it doesn't depend on coordinates. A similar thing is how you can see the integrability of J. The point is that if you look in geodesic coordinates, say G geodesic coordinates, then J will be expressed as a linear transformation. It eats vectors and spits out a vector, so it looks like this with some coordinate, with some matrix coefficients here, and the covariant derivative in geodesic coordinates is just the ordinary derivative, partial derivatives, at least coordinates centered at this point, M, and since the covariant derivative vanishes, that means that you can always choose coordinates in the neighborhood of a point so that the derivatives of j are 0. Now, the obstruction to integrability is this so-called Nine-House tensor of j, which, when you look at its formula, it's linear in the first derivatives of j. And since the first derivatives of j vanish in some coordinate system, that means the Nine-House tensor vanishes and at each point, and that's a statement independent of coordinates. And so, of course, that tells you that the Nine-House tensor is 0, and by the Nylander-Nirenberg theorem, that tells you that j is integrable, which is equivalent to the existence of these coordinates. So it's a very strong condition for a metric to have holonomy, to have unitary holonomy. It's kind of miraculous that there are any such metrics. In fact, the first question you have to ask is, do such metrics exist other than like the flat metric? You'll remember that Berger's theorem it's a limiting theorem. It says that the only things that the only groups that can be holonomy, possibly be holonomy, are these on this list. It doesn't say that these things actually occur. And so at this moment, if you didn't know this already, you might be wondering whether or not there could be metrics with holonomy, with unitary holonomy, other than flat ones. So, but the point that I'm going to emphasize is that we can now turn this question around and look at it from the point of view of prescribing the two form and the almost complex structure, well, the complex structure, since we know it's going to be a complex structure, and get the metric from that. So let's go back to the conditions needed algebraically on j and omega in order to get a g. You say that a almost complex structure in two form defined on M are compatible if two things happen. First of all, omega is supposed to be, as it was in the case that we had before, omega is supposed to evaluate on a vector and j times the vector to be positive for any non-zero vector. And second, that it should be omega and j should be symmetric with respect to omega. That is if you plug in this formula that we know is going to give us g when you work it out, this expression better be symmetric in V and W. So those are two algebraic conditions that you have to impose on a two form and an almost complex structure in order to get a metric. And in the case that those two conditions are satisfied, we say that this metric that's defined by this formula is the associated metric. And the critical proposition is this, that if you start with a compatible pair of a complex structure and and closed two form, so which we know we'd have to have if it was going to come from a G parallel metric, that if you take a compatible pair, J is integral and omega is closed, then J and omega are in fact G parallel, where G is this associated metric. So in particular, that says the holonomy of G is conjugate to a subgroup of UN. So this gives us a way of, well, it moves the problem, sort of like a bump under the rug. It moves the problem from finding metrics whose parallel transport satisfies some differential equation that makes it be unitary, that makes the holonomy be unitary, to finding pairs of an almost complex structure, well, complex structure, and a closed two form that are compatible. That's what it moves the problem over to that. And fortunately, those two problems are easily solvable. Well, and in fact, as you look at how the thing is proved, you actually start getting out a formula for what G must look like. First of all, since J is integrable, I mean, all integrable things are essentially equivalent. You can cover M with an atlas of J holomorphic charts. That is, charts like this, where the differentials carry J over to multiplication by I. That's the integrability. And then The second condition, which says that omega is basically symmetric in that J is symmetric with respect to omega. When you plug that into, when you look at what omega looks like in these coordinates, dz here, when you look at what omega looks like, of course, you can expand omega in three kinds of terms: dz wedge dz, dz wedge dz bar, and dz bar wedge dz bar. Those are the basis of one forms. And this condition tells you that there's no dz and dz bar terms. I mean, no dz terms and no dz bar terms. So there's only sort of the middle terms: dz wedge dz bar. And the fact that omega is real tells you that it has to be expressible like this, where in these holomorphic coordinates, where H, this matrix H, is Hermitian symmetric and positive definite. That's what 1 tells you. Tells you this 1. And then this formula tells you that G actually looks like this. It's you know, when you just figure out, just do the algebra, it tells you that G is actually HJK bar times dz symmetric product with dz k bar. So far, we've used everything. I mean, we've used the integrability of J, the fact that they're compatible to get this far, but we haven't used the fact that omega is closed. Now, the closure of omega, when you work it out, actually shows that the H, this Hermitian symmetric matrix, is not arbitrary, but it allows you to introduce a potential that shows that in fact this is the complex Hessian, as they call it, of F. That is, it's the matrix of second derivatives of F with respect to Z and Z bar. And of course, for any F, that's a Hermitian symmetric matrix. So that's where you get to. And now the nice thing is that the converse is true. That is, if you start with, take a domain in Cn, take any smooth potential function such that this quadratic form is positive definite, then you can compute straight away that in the standard complex structure on here, and this 2 form are both parallel with respect to this metric, the Levi-Civita connection of this metric. In fact, it's not very difficult to do. The crucial point is to realize that you can choose your coordinates in a very nice way to make sure that the first partials of G are all 0 in these coordinates. And you can choose holomorphic coordinates at a point so that the first partials of G are all 0. And once you do that, that means that the connection is basically, you know, in those coordinates, they're essentially, not quite, but essentially geodesic coordinates. And because the first derivatives are 0, J has constant coefficients here, and omega will have its first derivative 0. So they'll both be, this little argument about being, first derivatives vanishing in a geodesic coordinate system forces them to be parallel. It'll tell you they're parallel. So it's a pretty straightforward calculation. It's basically, choose good holomorphic coordinates. So, so this, this proof that you can change the holonomy condition into a pair of differential equations for an algebraically compatible thing actually gives us a formula for what the metrics with unitary holonomy look like in some coordinate system. And there are a couple of consequences of this that are worth noting. The first is that that metrics in dimension 2n with unitary holonomy do exist, and they depend basically on one arbitrary function of 2n variables. This function f that we chose to begin with has no conditions on it really, other than that its Hessian matrix is positive definite, and that's it. So choose something like that, you get a metric with holonomy in unitary group, and positive definiteness of the Hessian matrix is this complex Hessian matrix is an open condition. The second thing that you can get out of this without too much trouble is that the generic such metric has holonomy equal to UN. So whereas at the moment all this would have shown, all our calculations have shown is that you can find good coordinates which you can see what the metrics whose holonomy is in UN look like. Now you can actually use this formula to say compute the curvature at one point. And if you choose f generically enough, then you look at the curvature, the value of the curvature at one point, and it fills out it generates the entire unitary group. So by the Ambrose-Singer holonomy theorem, the holonomy will be all of UN. So you can easily generate tons and tons of examples where the holonomy is everything. It is the full UN. Now, I've been avoiding the classical name of this long enough. I should admit what it is. These metrics with unitary holonomy are said to be Kähler metrics. And, well, technically to be completely to be completely unambiguous, you need to specify the metric and J in order to say that you have a Kähler metric. But of course, specifying G and J tells you omega, so I'll just put all the data together and say that all this data with the integrability conditions assumed defines a Kähler structure. And of course, these manifolds have been studied to death and are still being studied because they're the natural metrics that you want to be able to use whenever you're studying complex manifolds. They're the metrics for which, complex manifolds are of great interest if you haven't already been convinced, you will be convinced by the end of Lou's lectures. Of great interest because of their connections with algebraic geometry, differential equations, mathematical physics, you name it. They show up everywhere, and just like ordinary manifolds are, without a metric on them are kind of slippery and don't have a whole lot of structure to them. Complex manifolds without a metric are also similarly seem to have, they're a little bit more difficult to study. So you want a metric, you want a good one, and choosing one for which J is parallel is in some sense the best you can hope to do. Of course, you can't always do it. There are plenty of complex manifolds that don't carry any Kähler metric. We'll see a little bit more about that a little later on. But one of the most important examples is complex projective space. This is an example of in fact, this is a Riemannian symmetric space. It's easy to check that its holonomy is all of UN. And so it has there's the unique metric on this guy that's invariant under SUN plus 1, unique up to constant multiples, is the sort of the complex analog of the sphere. It's the roundest Kähler metric you can get. And one reason, of course, that this particular case is so important is that in algebraic geometry, one is always studying rather than affine manifolds. You always like to complete them to something compact, and usually you complete them by putting them in some complex projective space. And as soon as you do that, they start inheriting properties of Kähler manifolds. One of the reasons is, in fact, one of the most important properties of Kähler manifolds, and this is something that unfortunately will not survive to the other cases, is that every complex manifold actually inherits a Kähler structure. That complex submanifolds of a Kähler manifold inherit a Kähler structure just by virtue of lying in there. That is, if you just take the 2 form and pull it back to the complex submanifold, then that induces a metric. I mean, that 2 form is compatible with the complex structure in the sense that I said before, and it corresponds to a metric. In fact, it's the pullback metric, and it's still parallel. So, you can still get metrics with parallel complex structures by simply pulling back to submanifolds. Like I said, that's a very unusual thing. It's very fortuitous for us for complex geometry, because that means that the smooth points of an algebraic variety always carry a Kähler structure. In fact, that's one important thing. There's another important thing that you'll see the importance of much more strongly after this morning's second lecture, which is that the powers of the Kähler form, these normalized powers of the Kähler form, are actually calibrations. Something that, in fact, this is sort of the granddaddy example of calibrations. So this is Vertinger's inequality, which, well, I won't go into more detail about this because Blaine's going to be talking about this extensively for the next 3 days. But I just wanted to make contact with what he's going to say. And one of the consequences of the fact that these things are calibrations is that it implies that if you have a Kähler manifold and you have a compact, complex p-dimensional subvariety, then that guy is actually calibrated by this form phi p, and therefore it minimizes volume in its homology class. This allows you, for example, I mean, just this statement allows you to show that certain manifolds can't be Kähler. For example, if you take, or can't carry any Kähler structure, certain complex manifolds can't carry any Kähler structure. For example, if you take C2, take out the origin, and then divide by the action of Z, where how does M act on Z, Z1, Z2 is just 2 to the M Z1, 2 to the M Z2. This guy is topologically S1 times S3, and it's compact. It's complex because this action is complex, so it leaves the complex structure invariant on this guy, and so it passes to the quotient. You get a nice complex structure on this guy. And if you look at any line, say C1, its image in here is a torus, is a complex curve, a one-dimensional curve, but it's 0 in homology. I mean, its top homology class, the two-dimensional homology class, is 0 because there is no homology class here. And that implies that this guy can't carry any Kähler metric, because if it did, that image guy would be volume minimizing in its homology class, but its homology class is 0. So, and since it's not empty, I mean, it would have to have non-trivial volume for any metric. It shows that this guy can't support any Kähler metric. Simple observations like that. Other kinds of things that show up are because J is parallel, you can use J to decompose the K forms into, as Lou was saying yesterday, you can decompose it into eigenspaces of J acting as a derivation, into the PQ forms, that is, the forms that locally in coordinates are P dz's wedged Q dz bars. And this decomposition induces a decomposition of the exterior derivative. It breaks up as a round D and round D bar, where round D increases the dz degree and round D bar increases the dz bar degree. Because this splitting is parallel with respect to delta, that implies that lots of formulas that work in lots of formulas that you work out in the general metric actually split nicely up into pieces with respect to this decomposition. For example, the Laplacian turns out to preserve each of these pieces. It carries PQ forms into PQ forms, and harmonic forms can therefore be written as a sum of harmonic PQ forms. Something that the parallelness turns out to be the crucial aspect of, as in fact many years ago Chern pointed out in this paper on a generalization of Kähler geometry. Chern pointed out that anytime you have holonomy reduction, if you look at the invariant decompositions of the exterior forms under the holonomy, that is, break it up into its irreducible pieces, then the Laplacian commutes with those decompositions, and as a result, you get a very nice decomposition of the cohomology of a manifold with reduced holonomy, and you get lots of beautiful formulas that generalize these D and D bar formulas, and we'll see those things showing up in various beautiful and interesting ways in the later examples. Well, that's all I want to say about the unitary case, really. I mean, I could go on for years talking about the unitary case, but let's go on to something else. I want to compare it with the next thing down in the table, that is the special unitary case. One thing before I do leave the unitary case is I wanted to make a remark about its relationship with the sort of the general metric case. You know, in the general metric case, if you look at the curvature tensors for a general Riemannian metric, it splits into three irreducible pieces. There's the scalar curvature, the traceless Ricci, and the Weil curvature. This is not always irreducible for when n is 4. It turns out that splits into two pieces, but let's leave that alone for the moment. For the general n, the Weil curvature is irreducible. The unitary case, the curvature also splits into three irreducible pieces. There's again the scalar curvature, the traceless Ricci, and this guy, which is called the Bachner tensor in the general case. As we're going to see in the special unitary case, it turns out that which is a subgroup of codimension 1 in the unitary group, what you lose, since this is a subgroup of this, its space of curvature tensors has to be a sub space of the space of curvature tensors in the unitary case. It turns out that what you lose is exactly the Ricci curvature. That goes away in the special unitary case, and this guy is irreducible. A word about this notation. What this means the polynomials on CM, real-valued polynomials that are quadratic in Z bar, and their trace, their ZZ bar trace is 0. And that is an irreducible representation of SUM, and that is what the space of curvature tensors is isomorphic to. And so what I want to do is sort of, especially since these are a special, manifolds with holonomy and SUM are a special case of manifolds of holonomy and UM, so we'll be able to use what we know about those guys to get started on this and then see what extra data we need to, what extra restrictions we need to understand them and see what kinds of extra special properties we have. We already know one thing that shows up, which is that in the unitary case, we had the invariant forms were generated by, well, there's always one, by this 2 form, omega. In the special unitary case, of course, you'll have those guys, but in fact, we'll get 2 more forms in the mid-degree that will be used as generators that will turn out to be the generators of the special unitary guy, of the invariants for special unitary guys. And in fact, a very nice thing turns up that allows us to turn things around a little bit. In fact, in some sense, even simplify the construction that we made in the unitary case. So the special unitary case, back to the definition, it's the set of unitary matrices with determinant 1, with complex determinant 1, and the nice thing about the special unitary case, which is not true of the unitary case, is that, you know, in the unitary case, we actually had to have the metric and the 2 form to define the unitary group, or the metric and the complex structure to define the unitary group. In the special unitary case, it can all be defined in terms of differential forms. That is, if you just look at if you just look at the set of all linear transformations in R2n, thinking of Cn as R2n, if you look at the linear transformations that preserve this form, this complex valued n form, and this real valued 2 form, then in fact that's the special unitary group. It determines the metric, it determines the complex structure and the metric, just knowing these forms. The reason it determines the complex structure is because if it preserves upsilon naught, then the linear transformation has to carry the dz's into the dz's. But that's exactly the definition of being J-linear. If it pulls dz's back into some linear combination of dz's, then it'll preserve J. So now you have J, and once you have J and the 2 form, you have the metric. So that's how you get down to the special unitary group. And in fact, it's not hard to show that the algebra of the SUN invariant exterior forms is generated by these 3 guys: omega naught, upsilon naught, and upsilon naught bar. Or you could take just the real and imaginary parts of upsilon naught if you want to get just real generators. And those were the forms that were listed on in the table before. It's easy to see that there aren't any more forms if you just look at the Hodge decomposition in the unitary case. And now restrict to the special unitary group and ask, do any of those pieces decompose any further? And the only one that shows up decomposes any further is the N0 exterior power, and it just becomes a trivial representation, so it has a real and imaginary part. The rest of them stay irreducible. The rest of the irreducible pieces stay irreducible. It's not that the PQ forms are irreducible, but they break up into irreducibles that are non-trivial. Conversely, suppose you start with a real vector space of dimension 2n, and suppose you take 2 differential forms, one of degree 2 and one of degree n, on upsilon. This one's going to be complex valued, such that upsilon is decomposable and satisfies that it wedge its conjugate is not 0. And if that happens, then because upsilon is decomposable, it's a wedge product of complex 1 forms. And there's a unique complex 1 form. I mean, there's a unique complex structure so that those complex 1 forms are of type 1, 0. So that says, again, it's just exterior algebra. And that implies, so there's a unique complex structure so that upsilon is a wedge product of n 1, 0 forms. So upsilon alone is enough to determine, this condition is enough to determine a complex structure on V. And then suppose further that omega is real valued and that it satisfies this positivity condition, which is the positivity condition we had to have for a Kähler 2 form anyway. That satisfies the positivity condition and it's of type 1, 1. Both of these things need J to be defined. So we're constructing J from upsilon and omega. And we're constructing J from upsilon and then using that to impose further conditions on omega. And it turns out that if you have those two conditions, then there is a constant so that these 2 forms are in fact equivalent under some isomorphism of V with R2n. There is a constant lambda such that once you scale upsilon naught, these 2 are equivalent to this guy. So the algebra of these 2 forms, these 2 differential forms, exterior forms, is enough to recover the unitary algebra. And you can tell when you have got the right kind of 2 forms, the right kind of forms, by just applying these 2 algebraic conditions. So that's the little algebra thing. Now, suppose that you have a 2n manifold whose holonomy is conjugate to a subgroup of SUN. then because SUN is, of course, a subgroup of UN, that tells you that, that you have a parallel complex structure and a closed 2 form. And in addition to that, because we're in SUN, we know that it will support a G parallel complex valued N form, upsilon, that lives in the N0 forms with respect to J. And of course, because it's G parallel, it has to be closed. Now, if you multiply this guy by a positive constant, you can arrange that this guy is this multiple of omega to the n. And this multiple was chosen, by the way, exactly so that, because that's the multiple that works for omega naught and upsilon naught that I had to begin with. Omega naught to the n. So the point is you can always scale it that way. And of course, like I said, since it's G parallel, it has to be closed. And of course, it has to be co-closed, again, by the remarks I made yesterday. And I'm going to make a definition, which is this, that a pair of 2 forms, a pair of forms, closed forms on a 2n manifold that satisfy pointwise those conditions 1 through 3 that I listed, I'm going to say that constitutes a Calabi-Yau structure on M. Notice that it's defined purely in terms of differential forms, and the complex structure and the metric come algebraically. They're constructed out of those out of the differential forms. And the proposition that's the analog of the proposition we had before for unitary guys is that for any Calabi-Yau structure, the associated complex structure J is integrable, the associated almost complex structure J is integrable, and the forms omega and upsilon are parallel with respect to the associated metric G. So whenever you can construct a Calabi-Yau pair like this, you get a metric whose holonomy is in SUN. That's the and let me give you again a little argument. Again, I won't go into details. We can discuss the details privately if you want. I just want to give you a sense of how it's done. By hypothesis, because this upsilon satisfies condition 1, it can be written locally as a wedge product of complex forms that are, they and their conjugates are linearly independent, of n complex 1 forms, so they're linearly independent. And, and then J is defined by requiring that J be carried out to I by those forms zeta k. Of course, they're only defined up to a complex linear combinations, but that won't affect the definition of J. Now, the condition that d upsilon is 0, in fact, implies that you can make a basis change in the zetas so that they become closed. This is the Nylander-Nirenberg theorem. It's a non-trivial theorem, but it's actually slightly easier than the Nylander-Nirenberg theorem because you have the closure of upsilon, not just that the d zetas are closed under exterior derivative. Anyway, you get this. That implies that J is integrable, so that means there are holomorphic coordinates, so that the zetas are linear combinations of the dz's. And not only that, because it's closed, you get that d bar of it's 0, which tells you that the coefficient in front of the dz's is holomorphic, so the upsilon is actually holomorphic with respect to J. And in fact, now you can choose. Now you can just in holomorphic coordinates, you can solve a first-order different PDE to show that you can actually choose your holomorphic coordinates so that upsilon is actually 1 times the wedge product of the dz's. So you can always do that. So far, we haven't used little omega at all. But now, we have J, which we know is integrable, and we've already seen, back in the other argument, that the closure of omega now implied that locally you can write the function on the domain of these coordinate charts so that omega looks like this and g looks like this, where of course this matrix is positive definite Hermitian matrix. And then this equation here, equation 3, when you plug that into these two formulas into here, what you get are, well, the condition of positivity tells you that this is a positive matrix, and this equation, when the smoke clears, simply says that the determinant of this Hessian is 1. It's kind of not too surprising. If you just compute the nth power of this guy, you'll see immediately the determinant of this matrix coming out, and these factors these normalization factors are chosen so as to make that be 1. So that's what we get to. There exists local coordinate. So far we've gotten down to this. The function f is no longer arbitrary as it was in the unitary case. It satisfies a differential equation. And the beautiful thing now is that you can compute that if you take any smooth function that satisfies these two conditions, in particular satisfies this differential equation, then the metric that you get here not only has omega and j parallel, we already knew that because it was a Kähler metric, but then upsilon, which is dz, is parallel as well. Again, you can choose holomorphic coordinates to see that without any problem. And since you have a parallel volume form, that implies that the holonomy of the metric lies in SUN. So this argument not only proves this fact that it can be understood in terms of a 2 form and an n form, but actually gives you a local formula for what these guys look like. But now notice that it's not in terms of a quote-unquote arbitrary function, but in terms of the solutions of some differential equation. But that differential equation is very well, at least locally, this differential equation is very well understood because it's if you linearize it at a solution, say, then you'll see immediately that this guy is elliptic. It's an elliptic PDE for f, and local solvability for equations like this is in fact pretty easy to do. A consequence of the elliptic theory is that any solution of this equation with this positiveness condition, any solution of this equation is actually real analytic in coordinates. And so you can think of it, so if you want to fall back on the old classical real analytic approach, then this equation being a determined elliptic equation, you can actually talk about initial value problems. So I know it's weird for an elliptic equation, but you can do it. And so, for example, you can take a hypersurface in Cn, and you can specify basically the value of f on this hypersurface and the value of its normal derivative, and supposing that they satisfy the right inequalities, just some open conditions on those things. As long as that data is real analytic, there'll be a local solution to this equation thickening out in the hypersurface. It may not extend everywhere, but it will exist. So there are tons and tons of solutions to this equation. Basically, locally, they depend on 2 arbitrary functions of 2n minus 1 variables. You get to choose, like I said, f and its normal derivative along a hypersurface. And this leads us to an understanding of some of the basic local properties. The first thing is what I was just mentioning, that the general Calabi-Yau structure depends on 2 functions of 2n minus 1 variables. Real analytic functions, basically arbitrary otherwise, so some slight open positivity conditions. And such a metric is always real analytic in J holomorphic coordinates. Now, if you remember from what I said yesterday, when I was talking about the various different low-dimensional holonomies that Cartan had mentioned in his original 1925 paper when he introduced the ideas, he made this statement that just said that there are metrics with holonomy SU2 in dimension 4. They depend on 2 functions of 3 variables. And that's this statement here. The existence of such in the SU2 case, they depend on two functions of three variables. This is probably not Cartan's method of proof. In the first place, Cartan did not have the Nylander-Nirenberg theorem in his bag of tricks. That was not going to be proved for another 50 years, or well, 40 some years. But he did have a very strong collection of techniques for handling differential equations in the real analytic category, and presumably his method, although he never describes his method, presumably his method was some combination of those techniques. So we may never know. Also, again, because you get to choose this initial value essentially arbitrarily, these two initial values arbitrarily, you can see that you can rig the curvature to take essentially a large collection of values at, say, the origin at one point. And you can apply the Ambrose-Singer holonomy theorem and see that the generic solution will have holonomy equal to SUN. It won't be any so the generic guy has holonomy SUN solution. Of course, there'll always be special cases where it doesn't, but this is what you get. The associated metric is always Ricci flat. That's a consequence of this computation of the curvature that we saw before, that the curvature that would be the scalar curvature and the Ricci curvature don't exist in the case of SUN. So you get Ricci flatness for these guys, and in fact it's reversible in the sense that if you have a simply connected Kähler manifold for which the metric is Ricci flat, then it turns out that there's a parallel holomorphic volume form, and so this vanishing of the Ricci curvature as you go from UN to SUM is not just accidental. It's actually essential for understanding the relationship between unitary and special unitary. And finally, again, to make connection with what Blaine is going to talk about, is it turns out that that if you look at the real part of this parallel form, that also turns out to be a calibration on this Riemannian manifold. It's called the special Lagrangian calibration, which has become much studied in the last 10 years. Because of its apparent connection with mathematical physics and string theory. We'll say more about that later. And in fact, the set of things that it calibrates, the Kähler form and its powers calibrate complex things, whereas these things have to calibrate something sort of half-dimensional, that's real dimension n rather than complex dimension n. And in fact, they turn out to be more or less the things that are as non-complex as possible. They're as real as you can get. Their tangent planes are actually perpendicular to J times the tangent plane. But there's a lot of these things. In fact, it turns out, again, I don't know whether Blaine will talk about this or not, but one of the things that he and Reese Harvey proved in their original calibrations paper, a very nice fact, is that if you take any real analytic n-1 dimensional submanifold of M on which the Kähler form, the 2 form, pulls back to 0, then in fact it can be thickened uniquely to an n-dimensional guy that is special Lagrangian, is calibrated by this n form. So there are lots and lots of these special Lagrangian things locally. Their global structure, I mean, once you know that there's a lot of them locally and how flexible they are, their global structure becomes interesting. Their modular space becomes interesting. And in fact, that's what the physicists are concentrating on. I want to close by saying just a few words about one of the most celebrated theorems of the past century, I think, in differential geometry, the global existence theorem for for a special unitary holonomy. But first, let me mention one thing. It's one thing to know that there are lots of local solutions. It's another thing to ask whether or not there are any complete solutions. All the the things that I wrote down, sort of said, well, you just solve this differential equation known as the Monge-Ampere equation, by the way. Of course, the initial value problem is hopeless for being able to figure out what the global solvability is and things like that. I mean, generically, you choose your initial data, it'll thicken a little bit, and then it'll fuzz and run into mess. When you try to extend it, it just blows up or runs into singularities. But you can ask whether or not there are any complete solutions that have holonomy SUM. And Calabi came up with a very nice example, an example whose properties actually turn out to be really important for understanding global constructions of these guys later on. So I wanted to just mention this method, which is Calabi said, suppose we look for a rotationally symmetric example on Cn. So we start with, we're going to take our standard volume form dz, and we're going to take a 2 form to complete our Calabi-Yau structure, and take it in the form I over 2 round e bar f of, where f is a function of a single variable that is the squared distance from the origin. So that's rotationally symmetric, and we can calculate. We can calculate, first of all, well, will omega actually be a positive? Will it satisfy the positivity condition? Well, if you expand this out, you'll see that you have to have 2 conditions. First of all, f prime has to be positive. And second of all, this funny combination, rho f double prime plus f double prime rho, has to be positive. Those are the conditions you need to get omega to be a positive 1-1 form. And now if you put in this volume, plug it into this volume relation here, you'll find out, expanded out, you'll get this equation. This is a determinant. In fact, the eigenvalues of the matrix that you get here, they're n-1 eigenvalues of this guy and 1 eigenvalue of this guy. That's the, so the product, that's the determinant, equals 1. That's why those guys have to be positive. And this differential equation, of course, I mean, if you ever go back to your classical differential equations course, you can integrate this equation. It has a first integral, namely you just multiply by n rho to the n-1, and both sides become exact derivatives. You integrate, and this is what you get. So you get a first derivative. You get an equation for f prime, and if you actually look at it, you'll notice here that you don't need f as much as you need f prime. You can actually, if c equals 0, of course, this is, of course, f prime is 1. And if f prime is 1, then you plug this in here, you get the flat metric. So it doesn't tell you anything. If c is positive, then you get a metric that looks like this. Just solving for f prime, you plug it in, you get this. The metric looks like this. And you'll notice that this metric is not smooth at 0 if n is bigger than 1. If n is equal to 1, in fact, the various things cancel out, and it turns out that the apparent singularity goes away. It's actually the flat metric again. So it's not too interesting. But if n is bigger than 1, this thing is definitely singular at 0. And so, and you might think, well, maybe that's not so bad. Maybe if we just throw away the origin, it'll be complete on the punctured Cn. Because it's easy to show that this metric actually is complete as you go out to infinity. I mean, any curve that goes out to infinity has infinite length. Unfortunately, curves going into 0 have finite length. So it appears to be singular at 0. Well, and not just appears, it is. The form omega is not smooth. But if you compute the curvature, for example, you'll notice that the curvature doesn't blow up. The metric doesn't look like it's becoming singular. It's just that, there's nothing locally about the metric that tells you that it's becoming singular. And in fact, there's a clever way to get rid of that singularity, which is to do the following thing. What you do is you take Cn and you blow it up. at the origin. That is, remember what the blow-up is. The blow-up is you look at the lines through the origin